Welcome back to ECE 441A, 541A. Homework number 7 is due in a week. While I shuffle furniture, exam number 3 is, what's today? The 14th. Oh, Friday. No, homework number 7 is due on Wednesday, isn't it? Our exam is due on, or is coming up a week from today. This is Friday. We've had 2 Mondays this week, and maybe that's why I'm messed up. We now, hopefully you are more aware of the calendar than I am. Your project for 541, if you're taking that, is due on the 7th, and that's when your lab number 3 is due. And if we're lucky, we'll start talking a little bit about some of the control strategies. We've already looked at phase lead, which is one of the control strategies for lab number 3. We want to talk about PID, which is the third strategy, or the next strategy that you'll use in lab number 3. In terms of office hours today, somebody's been bumped. I've been moved into another appointment at 9:30, so I just have 30 minutes after class today. That's not the rest of the semester, that's just today, but things are getting a little bit hectic as the end of the semester rolls around. What I want to do today is summarize the first order controllers. We've talked about phase lead and what those look like relative to the pole zero locations relative to each other. Phase lag is just the opposite of that, and we'll see that in the S-plane. We'll then get into PI and PID, so you don't need to be calling these PI and PID controllers. You probably want to refer to those as PI and PID because those are referring to particular pieces of your controller, and in particular, PI is not private investigator, it's actually proportional integral control, and PID is proportional integral derivative control. And we have 3 different terms to manipulate in the second one, the PID, and PI is now you have a pole that's fixed at the origin, you have a zero and a gain, and so you really effectively have 2 adjustable parameters for the PI controller. In terms of first order controllers, they both have this same expression for G sub C of S, or this same first order numerator factor, first order denominator factor. We have a gain. We're interested in locating a pole. We're interested in locating a zero and choosing the gain K. That structure is the same for both types. It's just where do you locate your zero relative to your pole. This first one that I've sketched in the S-plane, and this is just the controller. I haven't superimposed the plant at all. I'm just talking now about the structures of the poles and the zeros. What kind of a controller type is this location, relative location of pole and zero representative of? That's the phase lead that we have talked about already. This is now our phase lead controller, and we said that if we locate our zero closer to the imaginary axis than the pole on the real line, that has, in general, a tendency to improve our transient behavior. Where our transient might be we want to improve our percent overshoot, maybe we want to speed up the system by means of adjusting the transient or the settling time and maybe the peak time. Those are possible with this first order controller in a phase lead structure where your zero is closer to the imaginary axis than your pole is. And then they're both in the left half plane. Contrast that with this structure, look at where the poles and zeros are. Here the zero is closer to the imaginary axis. In this particular strategy, the pole is closer to the imaginary axis, and sometimes it will be right at the origin, but this is now a phase lag controller design. We have the same transfer function, g sub c of s, k times s plus z over s plus p, but now the p and the z, in terms of their relative magnitudes, have been changed, and that pair of poles and zeros in a phase lag, a lot of times those can be fairly close to the origin, both of them. And you're really just playing, when we get into a Bode plot-based design, you're really playing more with the separation of the pole and zero. They're both going to be close to the origin. The distinction of the phase lag controller versus the phase lead. The phase lead gave us transient improvement. The phase lag now can be used to enhance the steady state accuracy. Meaning, what is our steady state error? How do we track a signal? Whether that signal is a constant, a ramp, we might be interested in trying to get close to it. We may be wanting to be locked onto it. That will then be suggesting that you might want a lag type behavior in your controller. Let's look at a specific lag design, which is the PI controller design. This is a particular phase lag design. It's a proportional and integral controller, and in terms of the way you can think of it, you can think of it as two parts that now take the air signal coming out of maybe the summing junction that might be comparing the reference input to the output. You take that air signal, and in one path you simply scale it by a gain k sub p. That's the proportional path. Path, you take the same air signal, but now you integrate that air and feed that back, or sum that with the scaled air, and now you get this combination of a controller and that entire combination of two pieces of adjusting the air is now this k sub p plus k sub I over s. That is, in this dashed box, is now our transfer function that models a particular type of controller, and that's a proportional integral or a PI controller. Connecting that with what you've been seeing so far, we've been talking about having a plant. We apply some reference input to that, and now here is our controller, G sub C of S, that we want to now introduce into our, here is our air, here's U, and here's Y. This is now our closed loop system that would incorporate any controller G sub C, but now let's look at a specific type of controller, the PI controller. Is it clear what we're doing? Somebody might hand you a G, which in the lab, that's your mass spring damper system, and now they say, I want you to compensate that. I'm maybe not that happy with the behavior of your system. How do you build, how do you select poles and zeros and gains to place in that controller block G sub C? G sub C, let's see if we can rewrite that a little bit differently. We have G sub C as K sub P because that doesn't look like what we're used to seeing. We're used to seeing pole factors and zero factors and a gain, but we can manipulate this expression into that form. First, get a common denominator. We now have K sub PS plus K sub I. And now we do have a pole factor and we have a zero factor. We can explicitly pull out the gain that scales that S in the numerator, and now we have a gain, a numerator factor, which is going to determine our zero and our pole, and we might even just see this represented as K sub P S plus Z over S. Z is now obviously K sub I over K sub P. Another way of thinking of this is somebody might give you a controller and it has a proportional knob, an integral knob, and you now need to adjust those knobs. You now need to figure out, how do I manipulate K sub P and K sub I to produce the behavior that I want? What's the pole zero diagram of this? This now says that if somebody gives you or says they want a PI controller, you can now say, oh, that has a structure that looks like that. Boom. That's a PI controller. What does that look like in terms of the poles and the zeros that will introduce into the overall S-plane? Where's the pole of that particular controller? Right at the origin. So that gives us a pole right there. And our zero is somewhere in the left half plane. Here's minus C. And this structure, if you go back, oh, the pole is closer to the imaginary axis. Zero, that was what we were calling the phase lag design. This PI controller is a type of phase lag controller. Which means if it's a phase lag controller, it's probably trying to be used to enhance steady state accuracy. And we've talked about system type. System type, the larger the system type, the more signals really you'll be able to track, constants, ramps, etc. What does this PI controller do for your system type when you combine G sub C with a plant G? It increases it by 1, doesn't it? This puts one more integrator right at the origin. If you now started with a type 0 system, which might have a constant steady state error, somebody says, I don't want that steady state error. You go, okay, let me introduce an integrator. Let me give you a PI controller. Now if you can stabilize the system with that PI controller introduction, now you have 0 steady state error due to a constant, because you've now changed the system type to be bigger than what you originally had. Our strategy for designing a PI controller is as follows. If you want sort of a cookbook procedure, which there's a fair amount of flexibility in this, but first is to locate where is your 0. Where do you want to put that? And that's that Z, that's the numerator in your PI controller. You locate that, then your pole's already fixed for you. Once you decide on a PI controller, boom, your pole decision has already been made for you. It's right at the origin. Now you need to locate the 0, then you can determine the gain, locate your poles where you want them on the root locus, because once you have your plant and you have this controller structure, once you drop down the 0, you have all your poles and zeros. You now know what you can do. You can now sketch the root locus to see where are your closed loop poles going to live, and picking the K sub P will then pinpoint your closed loop poles where you want them. Once you have K sub P, then if you indeed do have some controller that has knobs on it, you found your gain of your proportional term, K sub P. Now you need to find your integral gain. But you can do that because you know this relationship between K sub P and Z. We have now, this is Z. If you set Z equal to K sub I over K sub P, you can now solve for K sub I. K sub I is just K sub P times Z. And you found both of those in the first two steps. Now you can adjust your knobs on your controller. Let's see if we can follow this through a particular example. Suppose somebody gives you the following system: S plus 1 over S plus 4, S plus 5. Now that you have that, and it may take you a fair amount of work to figure out what your plant is, what your transfer function is in the real world. It may take you some effort. That may not just fall off the turnip truck, whatever that means. It may not just fall into your lap. There may be a lot of effort in finding that G. But now that somebody or you've derived this G, what do you know about your system? What's its system order? Second order, isn't it? You have two poles. It's a second order system, and you know quite a bit about how a second order system likes to shake. How's this system like to shake if you just had it in the open loop? What are your modes? What are you going to see if somebody walks up and kicks this system or excites this system in an open loop fashion? What are you going to see happen or come out of that system? You have damping. Where are your poles? -4 and -5, right? Now, if you have modes that are associated with those poles at -4 and -5, what do those modes look like? E to the -4t and e to the -5t. Now we know what those sort of will look like if you just walked up and kicked that system in the open loop. Now, implemented this in a closed loop scenario, and you hit your system. Now maybe you would see, what's the system type? So we have system order, it's second. System type, is everybody okay that it's 0? System type is how many poles do you have at the origin? We don't have any, do we? This is a type 0 system. What does that tell us? How is this going to behave to a constant input? If this is, let's say, some physical system and it needs to go in a particular direction, or maybe you want it to move to 20 counts, is it going to go to 20 counts necessarily in a type 0 system? It may have a steady state error, won't it? Because it's not a type 1 system. So let's now introduce a PI controller to actually eliminate the steady state error. Due to a constant input. So somebody might say, I don't like the steady state error, and you go, okay, I'll eliminate that by increasing the system type. I'm going to give you a PI controller. Now you have to figure out where do you place the 0 and how do you adjust the gain on that controller to achieve some acceptable behavior. The PI controller is forcing that pole at the origin. You know that you now have a structure of K sub P, S plus Z over S. Now we can sketch most of the combination of our plant and controller in terms of its poles and zeros in the S-plane. Our plant, which I'll try to be putting in red in terms of poles and zeros, we have 1 0 located. Where is my 0 located in this plant? -1, isn't it? So I can now plot a 0 right there. My poles, you just told me for the open loop behavior, were at -4 and -5. And now if I told you to sketch the root locus of the uncompensated system, boom, you've got that done, right? That one's pretty easy. The pole at -4 is simply going to move towards the 0 at -1. The pole at -5 is going to go off to -infinity, and you have nothing else happening. There's nothing happening off the real line for that system. Now what you said is, oh, you weren't happy with the steady state error behavior. You've now said you wanted a PI controller, so now that forces a pole at the origin. That's going to be in blue, and now we have to figure out where to put our 0. And a lot of times you will say, oh, maybe I want or would like my behavior to be somewhere, and you pick a triangle location. In this case, I'm going to just sort of illustrate the process of picking a PI or designing a PI controller, and I'm going to somewhat arbitrarily simply place my 0 right there. But now what does that do? That eliminates one of those poles, and now again I have a pretty trivial root locus sketch to perform. I have this branch, and now I have this branch. What I did is I simply, for illustration purposes, let me say, let's select Z equal to 4. Whoa. Somebody got happy. to simplify the design. In general or usually, that 0 location, Z, is selected to help determine or achieve a specific S delta. But you don't have a whole lot of options here with this particular system if you're simply introducing a PI controller. You're not giving yourself a whole lot of options. But with a lag controller, you may be saying, I'm willing to sacrifice or slow down my transient. And you really have, haven't you? Because in the open loop, you had modes that were e to the minus 4t and e to the minus 5t. Where is one of your closed loop poles going to live now? Where? It's going to be stuck, isn't it, between the origin and minus 1. You have some, let's say, fairly slow pole relative to where you started with, which were poles at minus 4 and minus 5. But you're getting something. There's a trade-off. What are you receiving in return for slowing down your system behavior? 0 steady-state error. Now you're saying I'm more concerned for this system to give me accuracy in the steady state, and I can sacrifice a little of the speed in getting there. That's the trade-off, and as an engineer, you're always going to be playing with trade-offs. Now, the only thing left in this particular design is to actually find a gain K sub P in your controller, because we have already picked, well, we're forced with our pole at the origin. We picked Z. Now let's determine K sub P. Let's now select K sub P to produce a closed loop pole at S delta equal to minus 1/2. So now I'm saying I am actually going to be satisfied with a closed loop pole at that location. Where's my other closed loop pole going to be, roughly? Besides the one at minus 4, which is stuck because I canceled it. And if you canceled it precisely, you really won't see it much. You won't see it at all in the transfer function between the reference and the output. Where's my other closed loop pole going to be? To the left of minus 5. It's somewhere on that other branch of the root locus, and we're just going to be happy with where it goes. Is that going to give us a faster or slower mode than the mode at minus 1/2? Faster, right? So now the one, which triangle is going to dominate your behavior? On the right or the one on the left? Which triangle dominates when you now close the system loop? This is now, I'm assuming we've already found the gain K, which we haven't yet. But let's say we've now found the gain K. We now have closed loop poles at those two triangles. Which of those triangles dominates? The one on the right or the one on the left? Right is going to be up, left is going to be down. 1, 2, 3. Some people didn't put their thumb into the pie and pull out a plum, did they? Should have been up. The slower one, the one closer to the origin, is dominating. So when we say dominate, we're saying what's taking so long? It's not the one that's fast. It's the one that's slow. That dominates the transient behavior. Now let's figure out our gain k to put us at that location of minus 1/2. How do we do that? How do we find k sub p? You could simply sit there and adjust your knob, right? But we know that we can improve on that process. We don't have to infinitely adjust different k's. We can just use our magnitude condition to solve for the specific gain k. The magnitude condition says we have our controller times our plant and if it's on the root locus, we know the magnitude of g sub c g is equal to 1. We don't have to worry about that factor. That one gets canceled. And now we can solve for k sub p. That's now s plus 5 over s plus 1. And I evaluate that where? Where I wanted that triangle. And now I have my controller. G sub c of s is equal to 4.5 s plus 4 over s. And if somebody says, well, I have a box that has two gains on it, a p gain, a proportional gain, and an integral gain, and you're giving me that transfer function, how do I find k sub p and k sub I? Well, we know k sub p, that's 4.5. But if we multiply this out, we have 4.5s plus, what's 4.5 times 4? Well, 4 times 4 is 16, and then a half of 4 is 2, so that should be 18 all over s. And if I simply divide that out, I have a 4.5 plus an 18 over s. And that now is in a structure that I can explicitly identify gains. There's k sub p, and 18 is k sub I. Can you tell me what the settling time is for that designed controlled system? My 2% settling time? With a controller of 4.5 times s plus 4 over s and a system, second order system, controlled with a PI controller, what's my settling time? And what influences settling time? Your poles, doesn't it? Your closed loop poles, and we've already determined which one is the dominant closed loop pole. That's the one that's going to impact our settling time the most. The other one's going to go so quick that it's not going to impact our settling time. And where was our slowest pole? Where was our triangle that was the slowest? That was at minus 1/2, wasn't it? We now have the information that we need. This is 4 tau, or 4 over sigma. We know our sigma of the slowest pole was at 1/2. It will now take us 8 seconds to get to our final value, but we will have 0 error when we get there. that clear? Now, somebody might say, well, I'm not real excited about that speed of response, and they say, can you improve on that? And now you say, well, I have to add another consonant. So you now spin the wheel, and you get to pick a D, a derivative. That derivative is going to help you improve your transient. The PI worked on the steady state accuracy. The D is going to improve the transient. This is now a proportional integral and derivative controller. We have the P, the I, and the D. The I term we were using for accuracy. The D term, the derivative term, is going to help us with the transient. And if we now look at a PID controller, we already know the first two pieces. We have a case of P, we have a case of I over S. That's the P and the I. And now we would anticipate a case of DS. Now that's not going to be very nice in terms of behavior at high frequencies. In practice or in reality, we actually put in a pole factor where that P is maybe pretty fast. So in reality, or in practice, you're going to have a pole underneath that case of DS term, but it's going to be really, really fast relative to everything else. So in design process, we're going to neglect it. We'll just have a case of P plus a case of I over S plus a case of D times S. What's the Bode plot of this look like? Case of D S over S plus P. We're going to have to start remembering our Bode plot stuff. If I now said, what's the magnitude of this in dB? Do you remember anything about Bode plots? We need to worry about the different factors, zero factors and pole factors. And if we're just worrying about magnitudes, we have linear factors, which just means we have first order factors. We have one zero here, and we have one pole. What's the pole do to us in terms of behavior of the magnitude of our Bode plot? It gives us a slope of minus 20 dB per decade, doesn't it? Down. Because it's downstairs. It's in the basement. That's our pole factor. So it's going to produce a sloping magnitude with a magnitude slope of minus 20 dB per decade. And where does that kick in or break? Where does that slope begin in terms of frequency? It appears right at the pole, doesn't it? So that begins at the pole. Now let's go up to the zero. If we had an S plus Z, that would be similar. It's just now it would be upstairs and it would be going up and it would break at Z. We don't have a Z. It is nowhere to be found. We just have an S. This is now a zero at the origin. Do you remember what happens when we have poles and zeros at the origin in our Bode plots? Well, it's a zero. It must be going up. And we never, never, never break, so it's never going to stop sloping. It never starts. It never stops. Yeah. It's just going up at 20 dB per decade, always. Now it crosses a particular point if it was all by itself, but now we know in terms of the behavior, this is coming up from the bottom because of that 0 at the origin. And then once we hit, and that's actually our derivative action, that's now enhancing signals at higher and higher frequencies. We don't want really high frequencies to be excessively exaggerated. So now we have this break due to the pole, and if we needed to orient where that break occurred, we know it occurs right there at P. Derivative action would say, oh, just keep increasing the gain as you go higher and higher in frequency. That would be the K sub ds. But we know we don't want to keep doing that because we may have high frequency noise or high frequency signals entering our system, so we want to roll that off at high frequencies. That's why we put that in reality piece there. We're going to neglect that in our design, and if we do, we now have this K sub P plus K sub I over S plus K sub ds. And now we know how to rewrite that to give us an expression that we like to work with, which are pole factors and zero factors. If I now put all of those over a common denominator, I just have one denominator piece, and that's the pole at the origin due to the integrator. Let me keep the order of my s's, let's say from highest to lowest. I'm now going to increase everything in the numerator with a power of s. I now have a K sub d s squared plus a K sub p s plus a K sub I. And if I factor out that K sub d, I now have an s squared plus a K sub p over K sub ds plus a K sub I over K sub d, all divided by s. That's now my generic structure for a PID controller. How many zeros do I have? We have a second order numerator. We have 2 zeros. I only have one pole, and that's fixed. That's right at the origin. That's due to my integrator. These 2 zeros, depending on how I pick K sub P, K sub I, and K sub D, these could be either real or complex conjugates. Meaning, if I looked at the 2 different pole zero patterns of this PID controller, if I now had real zeros, I know where to put the pole. That's easy. And now I might have a 0 there and a 0 there. That's one possible configuration of a PID controller. And what do you have flexibility in selecting? Design. Now you're designing. Which pieces of that design do you have flexibility over? It's the zeros. You get to slide those wherever you want. And you could even have Z1 and Z2 equal. Don't have to be unequal. If I looked at the complex conjugate zeros, now I have something like this, where this distance into the left half plane is A, and let's say that it has an imaginary piece of B. if you now were asked, what's the transfer function for this PID controller right here, how would you express it? You know the gain K sub D and you know the pole. But you've now said that you're picking one 0 there and another 0 there, and that's now how you would parameterize your PID controller for that structure. And then you could multiply that numerator out, equate coefficients, and now you would have the ability to find K sub P and K sub I. We need to make a little bit more noise, apparently. We're not loud enough. Raise up the ambient noise, and then I'll adjust it with a gain, right? We're adjusting gains. What's this one on the right look like as far as a transfer function? I'll do the hard part. We still have the gain, K sub D. We have a pole due to the integrator. But now you should be very comfortable with expressing complex factors. You now know that you have the real part is going to be associated with this S plus A quantity squared, and the imaginary part gives you B squared. You can now multiply those out in the numerator and equate and find K sub P and K sub I. What if I gave you even a third option, which I probably will do in the demo for lab number 3? What if I now said, oh, here's a PID controller structure. What's the transfer function for this guy? Well, you could say, well, it's just like the one on the left. Z1 equal to Z2. That's correct. That's what you have. And you can now multiply that out and solve for K sub I and K sub P. That information implanted now in your brain. Lab number 3, we're going to continue to play with the same system. Let's just, for illustration purposes, assume that the system that we're dealing with has open loop poles at -2 plus and minus J20. And your system may be a little different, but it might be close. Maybe it's -1.5 plus and minus J15. But it has that same pattern. That's now your mass spring damper system in the lab. If you now said, oh, I want to apply output feedback, what would happen? What would the root locus of this system be? What's the root locus of this with pure gain feedback? What part of the bread am I going to be keeping? I have now this long, infinitely long French bread on the real line. I want to cut it up, slice it and dice it. This is an infomercial. We're cutting up this French bread and handing out the pieces. How many cuts do I have? Do I have any poles and zeros on the real line segmenting that real axis? No. So there's nothing going to happen on the real line. That infinitely long French bread stays. where am I going to have root locus branches? Shoot, rule 2 or whatever didn't apply. Do I have rule 3? What's my pole zero excess? 2. What's the pole zero excess do for us? It tells us we have asymptotes, doesn't it? And what's the fundamental angle of one of our asymptotes? 180 divided by that pole zero excess of 2. What's the root locus going to do? And where's the centroid of that? It's sigma sub A is minus 2 divided by 2 minus 2. The root locus is that. So now as you crank up the gain K, what happens to your system? It oscillates faster and faster without any improvement in the damping. Your settling time is the same. You just maybe get there quicker, but you now shake faster. Maybe you don't like that, and we'll figure out what happens when we introduce PI and PID controllers to lab number 3, maybe next time.